by the way, what I just said in Russian, today's the reference for today's class is theorem something from Hatch's spectral sequences, which can be found on Hatch's webpage. Okay. Now, we use this lemma to prove this implication for K. To prove 1/2 of part 2 for K by n's for n greater than 1. Well, we use the path loop vibration. The path loop vibration for K pi n plus 1 looks as shown here. And we have a similar vibration for K pi tensor Q n plus 1 K pi tensor Q n. Does this diagram make sense? N plus 1, sorry, there's a Q here. Well, it doesn't matter. Well, it doesn't matter. One could take n plus 1, n plus 2, or any other two adjacent numbers. Let's see. The fiber of the path loop vibration is the loop space. Yes. So the loop space of K pi n plus 1 is K pi m. It's not the other way around. Okay. So we have this diagram. Does the diagram make sense? Okay, so the Well, the first observation from the lemma, we conclude that we conclude by induction that the integral homology of k pi n plus 1 z is in fact a Q vector space. So this proves one part of what we need to prove. To prove oh, and by the way, the homological triviality condition is automatic. Why? Because this space is simply connected. Now, we need to prove that this map is an isomorphism, and well, let me write it here. So we have hk pi n plus 1 tensor q, which is the same as hk pi n plus 1 with q coefficients. Okay, let me write here a q first, but then this is the same as hk pi tensor q n plus 1 comma z. So this map is an isomorphism. Here is where we use here is how we use the spectral sequence. The spectral sequence also has the 2 out of 3 property, meaning if we have a map of vibrations and both vibrations are homologically trivial, which is automatic since each of the bases is simply connected. If we have an isomorphism for the map of the reduced homology of the fibers and of the total spaces, the map of the reduced homology of the bases is also an isomorphism. So basically, base plus total space implies fiber. Fiber plus base implies total space. Total space plus fiber implies base. 2 out of 3 implies the third one. We know that for 2 of those we have basically for the base, for the fiber and the total space, we have isomorphisms with Q coefficients. So we have an isomorphism with Q coefficients for the bases as well, and this this completes the proof. Are there any questions, objections, criticism? Okay, now the proof of so we're still trying to prove one implication of part 2. And the proof for more general spaces is very similar. We will need the lemma again, so I'm not erasing it yet. So for general abelian X, we have a Q localization, and we need to prove what we've just proved for Raleigh-Bach-MacLane spaces. So we if we have a map XX prime, we have a map Xn to X prime n for all n. Okay, so since we since we have so let's recall that since the space is abelian, xn plus 1 is fibered over xn, and this fibration is induced by the nth k invariant. In other words, by a map from xn to k something something. Similarly here, this is a vibration which is induced by blah blah blah. So the fiber is okay. Sorry. No. This time I need the indices pi n plus 1, pi n plus 1. N plus 1, comma, n plus 2. Tensor Q, comma, n plus 2. Okay, so both vibrations are induced from the path loop vibrations. The map of the basis, the map of the vibrations induce the map of the fibers of the vibrations, and we get this commutative diagram. We proceed as we've just did for Eisenberg-MacLane spaces, but we need to check that these vibrations are homologically trivial. Now, the action of pi 1 of k pi pi 1 of xn, which is the same as pi 1 of x on the fiber. Well, let me so this action exists only up to homotopy, but then if since our space is a k by n, then the action is determined by on pi n plus 1. Which is just pi n plus 1. And our space is abelian, so the action is trivial. And similarly, for x prime, we have well, x prime is by definition abelian, so the same argument applies to x prime. And now we use the lemma to conclude that the homology of x n plus 1 is a Q vector space. And and we use the Leray spectral sequence with Q coefficients to conclude blah blah blah. What is blah blah blah? Blah 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 is that this map is an isomorphism for xn. Let me write this down somewhere. I'll erase this, but okay, I should have erased the lemma. This is the last time we've used it. But anyway, so the Leray spectral sequence with Q coefficients implies that the map of the reduced homology x n plus 1 prime, no, x n plus 1, just tensor Q to the reduced homology x n plus 1 prime is an isomorphism. So starting from n equal 1, we conclude that this map is an isomorphism for all finite stages of the Postnikov tower. And basically the homology of x is the same as the homology of any given degree homology of x is isomorphic to the homology of some finite stage of the Postnikov tower in the same degree. Well, I don't remember it's approximately the same I, but since I don't remember the exact value, I just write greater than approximately. Anyway, finally, I think we have proved one of the implications of the second part. Do you agree, disagree, or partly agree, partly disagree? Значит, значит, отображения из KPN в KPN, они, значит, они определяются отображением из P в P. То есть если мы знаем, как отображение действует на P, то мы знаем, как оно действует на всем KPN. Вот, ну, хорошо. Значит, а что такое, значит, Pn плюс 1 от KPN? Ну, это вот P. Are there any more questions? Okay. Well, now that we have proved 1/2 of part 2, let's prove part 1. Localizations exist. And the idea is to well, the idea is to tensor the Bosnikov tower by Q. But how to make it precise? Well, let's start with an abelian space. X1, which is a k pi 1, k pi 1, 1. We already know how to localize abelian spaces, k pi 1s, so we start with this map, and we declare the x1 prime to be the k pi 1q1, and this map is a Q localization basically by definition. Okay, so I have this this diagram where K1 is the first K invariant. What do I do with it? well, this map is this one. This map is just induced by tensoring by Q. Good. Now, my claim is that this there is a map from x1 prime to k pi 2 tensor q3, which makes the diagram homotopic commute. Why? And here we use obstruction theory. This map exists. And moreover, which we will need for part 3, not only it exists, it's unique. Why? Let's think about this map as a cofibration. So x1 prime, comma x prime, comma q. My claim is the result is 0. Actually, let me write it slightly differently. In order to construct an extension of this map to this space, I need to calculate the relative homotopy groups, relative homology groups, with coefficients in some homotopy groups of the target space. Well, the target space is k pi something something. There is just one homotopy group. This one in degree 3. Well, it doesn't matter in which degree it lives. What matters is it's a Q vector space. And this relative homology group is 0. Why? Because the homology map or reduced homology map, in this case it doesn't matter. The reduced homology map from x1 to x1 prime with q coefficients is an isomorphism. And here we use the half of part 2, which we already proved, and we use the fact that x1 to x1 prime is a Q localization. So there are no obstructions to extending this map to x1 prime. And moreover, the extension is unique up to homotopy. Basically for the same reason. the relative homology groups are identical as 0. Okay. So we have this diagram. This induces a map of the path loop vibrations. Well, more precisely, the map of the pullbacks of the path loop vibrations. We have a path loop vibration on this space. Pull it back, we get this vibration. We have the path loop vibration on this space. Pull it back, we get this vibration, where x2 is the fiber. The fiber of what? The fiber of the pullback of the path loop vibration of this space to x1 prime. Okay, does this make sense? Some sense, no sense, or anything in between? Some sense. Okay, so once we have this diagram, this part of the diagram, and the part homotopy commutes, we get a map of the pullbacks of the path loop vibration, and this gives me a map of fibers, and I just denote the fiber of the second vibration by x2 prime. Now, the claim is x2 prime is a Q localization. Why? Well, basically, basically, I need to compare two long exact sequences of the homotopy groups. I have one. I have one for the top row, and I have one for the bottom row. And the map from the top row to the bottom row is not an isomorphism, but it becomes 1 after tensoring the top row by Q. Why? I take the top row. Q is a torsion-free abelian group. So tensoring by Q is exact. In fact, tensoring by Q is the same as localization for localization of abelian groups in all positive integers. And we know that localization is an exact functor, but here we don't need to use it. We can just use the fact that Q is flat as a Z module. Why? Because it's torsion free. So we take the top vibration, take the long exact sequence of the homotopy groups, tensor it by Q. The sequence is still exact and still long. And after I tensor the long exact sequence by Q, the top one, I get it still maps to the bottom one. Sorry, before I claim that the top one tensor Q maps to the bottom one, I need to know that the homotopy groups of X2 prime are Q vector spaces. Otherwise, I don't have this map. If I have a group which maps into another group, there is no guarantee the first group tensor Q will map to the same group. This is only true if this is only guaranteed if the target group is a Q vector space. Well, this follows from basically from the 5 lemma. Suppose I have a sequence of groups A, B, C, D, E. And suppose I want to know that whether or not multiplication by M as a map of this exact sequence to itself is an isomorphism. Well, if it's an isomorphism for A, B, D, and E, it's an isomorphism for C by the 5 lemma. Okay, now what does this give me? This gives me the following thing. If all groups, except maybe the middle one, are Q vector spaces, so is the middle one. And as a result, I conclude that the homotopy groups of X2 prime, X2 prime are Q vector spaces. And now I have this map. well, in order for the map to be an isomorphism, we need to tensor the source by Q. Otherwise, we don't necessarily get an isomorphism. So once I know that the bottom that the homotopy groups of the bottom row are Q vector spaces, I have this map, and this map is an isomorphism again by 5 lemma. Which means, in particular, it's an isomorphism for the homotopy groups of x2 tensor Q and the homotopy groups of x2 prime. So we conclude that x2 to x2 prime is a Q localization. And then we basically continue in the same spirit. And we construct xn plus 1, xn, k n plus 1, n plus 2. We continue in the same spirit, and we get a sequence of xn primes such that every xn prime localizes xn, and basically this is it. After we have all the xn primes. We just take x prime to be a CW approximation of the inverse limit or another option would be to say that all xn's are sufficiently nice, in fact so nice, that it makes sense to consider the homotopy limit. And this would work if xn's are polyhedra or something more general, but not too much general, such as the geometric realizations of simple sets. In which case, the homotopy limit makes sense, and this particular strategy may be something that some people may prefer. Are there any questions?
Why xn plus 1 prime or construct using Euclidean space?
Well, we basically proved the theorem a couple of weeks ago that if a space has a tower of principal vibrations, and if by 1 is a billion, then the space itself is a billion. Well, let's assume by induction as induction hypothesis that this space is a billion. This space has a tower of principal vibrations. Well, we construct the next one by pulling back the part of the vibration from this by construction. So the next one has also by construction has a tower of principal vibrations. Are there any more questions? Well, we'll probably need to finish soon. Let me say a few words about proving part 2. So, are there any? I think we have proved part 1. Does everyone agree? Let me briefly say something about part 2, the other implications. So, if I have a map of a billion spaces such that, then it's a Q localization. Let me take any Q localization, and let me take a map of a billion spaces x to x prime such that the homology of x prime, the integral homology of x prime is a Q vector space, and the homology map of the map of the homology of x tensor Q to the homology of x prime is an isomorphism. Let's deduce that x prime and x double prime are in fact homotopy equivalent, and this will prove that since the first map is a Q localization. Since the second is a Q localization, the first one is one as well. And we use obstruction theory. So there exists this map by obstruction theory. Well, the trick is exactly the same as the one we've just used, namely there are no we have this map, and there are no obstructions to lifting it to this space, and this map induces an isomorphism of the homology groups tensor Q, but the homology groups tensor Q in both cases are the integral homology groups. Why? Well, for the first map we have this by assumption, and for the second map we have this by the other implication of part 2. So the vertical map induces an isomorphism of the integral homology groups. And it's a homotype equivalence because all spaces are abelian. Okay, so I promised to finish a little sooner than usual, and I think I've kept the promise. Are there any questions on what we've just done? And by the way, a couple of weeks ago, some of the participants were surprised to hear that if we have a map of abelian spaces which induces an isomorphism of the homology groups tensor Q, it also induces an isomorphism of the homotype groups tensor Q. Well, now we know why. So it's not very surprising anymore. Are there any questions? Okay, so this is it for today, and well, next time we'll start talking about commutative algebras, which is one of the ways, commutative differential graded algebras, which is one of the ways to algebraize rational homotype theory.